Okay, so the question is, how many of these molecules are polar? And you're given 1, 2, 3, 4, 5 different molecules that you have to figure out. So an overview of what we're going to do is we're going to draw the Lewis structure of the molecule, and then we're going to identify the bond dipoles using their differences in electronegativities, and then we're going to identify the net molecular dipoles using its molecular geometry. So to start off, we're going to start with the molecule SO3. SO3 has 24 valence electrons. So we're going to start by drawing the Lewis structure. So sulfur is going to be your central atom, with oxygen with the 3 oxygen atoms being the outside atoms. I already have my bonds drawn. So now let's start making octets out of the oxygen. Here we go. Okay, so let's check to make sure we have octets. 2, 4, 6, 8. That one is 2, 4, 6, 8. That one is 2, 4, 6, 8. And that one is. So let's see how many total valence electrons we've used. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've used all of our valence electrons. Yet sulfur still does not have an octet. So in order to allow sulfur to have an octet, we're going to make this a double bond. There we go. So now let's check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and all of those have octets. So now we're going to draw the bond dipoles. Since oxygen has a greater electronegativity, all of the oxygens are going to be slightly negative. And that makes the sulfur slightly positive. Okay, so from here we're going to draw our bond dipoles. So this bond dipole is going to go this way. This one will go this way. And this one will go this way. So bond dipole, bond dipole, bond dipole. Okay, so now we're going to create the molecular geometry. So since there are 3 domains, 1, 2, 3, we are going to have a trigonal planar because there are no non-bonding on the sulfur, so it's just a regular trigonal planar. So the next question is, will all of the net molecular dipoles cancel out? Here are your net molecular dipoles. Will they cancel out? The rule is, if all of the 3 domains are equal, then there will be no net dipole. So oxygen is equal to oxygen is equal to oxygen, so all of the net molecular dipoles are equal. So there's no net dipole. And since there's no net dipole, that would make this molecule non-polar. Okay, so that's SO3. Now we're going to move on to OF2. OF2 has 20 valence electrons, so we're going to draw our Lewis structure. It's drawn. So let's just make sure that we did it right. 2, 4, 6, 8 octet, 2, 4, 6, 8 octet, 2, 4, 6, 8 octet. And let's see if we use all of our valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So all of our valence electrons were used up. All of our atoms have octets. So now let's look at our bond dipoles. So F has a greater electronegativity than O. So the fluorines will be slightly more negative than our oxygen, which is going to be slightly positive, which means that our bond dipoles will go from the oxygen to the fluorine, from the oxygen to the fluorine. So now let's draw our molecular geometry. So there are 4 domains. 4 domains, which makes it a tetrahedral. But since two of those domains are non-bonding or lone pairs, it's not going to be a regular tetrahedral. We're going to have a bent molecular geometry. So here's our bent molecular geometry with our 2 non-bonding domains. And since our domains are not all equal, this is not equal to this, and this is not equal to this, so our domains will not be able to cancel out. So there's going to be a net dipole, and the net dipole is going to go straight down. And because there is a net dipole, the molecule is going to be polar. There we go. So that's OF2. So the next molecule is going to be BeCl2. BeCl2 has 16 valence electrons. So to create our Lewis structure, Be is going to be your central atom, Cl is going to be on the outside. So let's see if we fulfilled our, if we used all of our valence electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16. So we've used all of our valence electrons. But one might say that beryllium does not have an octet. Well, beryllium is one of those atoms that is allowed to violate the octet rule. So after that, we're going to determine the bond dipoles. So Cl has a greater electronegativity than beryllium. So chlorine is going to be slightly, the chlorines are going to be slightly more negative than beryllium. Beryllium is going to be slightly more positive. That's a negative, not an electron. So your bond dipoles are going to go from beryllium to chlorine, from beryllium to chlorine. So now let's look at our molecular geometry. So there are 2 domains, 1, 2, which would make it linear. So here's our linear molecular geometry. And because the molecule is linear and the two domains, Cl and Cl, are equal, there's going to be a no net dipole. So these dipoles are going to cancel. And because there's no net dipole, that makes BeCl2 non-polar. Okay. So now we're going to do CCl4. CCl4 has 32 valence electrons, my bad. So start by the Lewis structure. So carbon's going to be our central atom with the 4 Cl's on the outside. So let's check to make sure that we use all of our valence electrons and that all of our chlorines have octets and our carbon has an octet. So we have 2, 4, 6, 8, that's right, octet. 2, 4, 6, 8, that's an octet. 2, 4, 6, 8, that's an octet. And 2, 4, 6, 8, that's an octet. So our Cl's all have octets. 1, 2, 4, 6, 8, and so does our carbon. So let's make sure all of our valence electrons were used. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So all of our valence electrons were used. So now we're going to draw our bond dipoles. So since chlorine has a greater electronegativity than carbon, our carbon is going to be slightly more positive than all of our chlorines. All of our chlorines are going to be slightly more negative than our carbon. So our bond dipoles are going to go from carbon to chlorine, from carbon to chlorine, from carbon to chlorine, and from carbon to chlorine. So that's your Lewis structure with your bond dipoles. So now we're going to do our molecular geometry. So there are 1, 2, 3, 4 domains which would make this a tetrahedral, and there's no non-bonding, so it's a tetrahedral in the molecular geometry as well. So the rule is if all the domains cancel out, if all the domains are equal, they will cancel out. So all of the Cl's are equal to one another. So there's going to be a no net dipole on this molecule, which makes CCl4 nonpolar. So that's CCl4. Okay, so now we're going to do O3 or ozone. Ozone has 18 valence electrons, so you're going to do your Lewis structure. So let's make sure this one's right. 2, 4, 6, 8, 10, 12, 14, 16, 18, and all of the oxygens have octets. So then we're going to go to the molecular geometry, and the central oxygen has 1, 2, 3 domains, so it's going to be trigonal planar, but the molecular is going to be bent because one of those domains is non-bonding. So then, because the domains are not all equal, it has a net dipole, which is going to be right here, which makes O3 polar. So back to the question, how many of these molecules are polar? SO3 was nonpolar, OF2 was polar, BeCl2 was nonpolar, CCl4 was nonpolar, and O3 was polar. Okay, some common mistakes to look for are to make sure that you have the correct Lewis structure, because this is a basic step that needs great attention because it can screw up your entire bond dipole and your molecular geometry structure. And don't just assume a molecule like O3 is nonpolar because all the atoms are the same. If you draw the Lewis structure and the molecular geometry to see if all the domains are equal, you'll see that for O3 they're not. So just because all the atoms are the same doesn't mean that the structure is nonpolar.